I'm going to do my other review session on Tuesday once I come back. So that's the way we're going to do this. Okay, perfect. Thank you guys for being so understanding and flexible. And it's just something I really want to do. So just kind of bad time. And I'm really glad we moved the test to Wednesday. So that's good. Okay, yeah, so basically, I don't want to go through the rewriting this whole thing backwards again. You start with this n naught greater than this in the natural numbers, right? And then if n is greater than n naught, then this is true, therefore this is true, therefore this is true, therefore this is true, this is true, and this is true. Right. Clear enough? It's a little bit technical, but...
you mind if you like skip like a whole bunch of the
Yeah. As long as I see the scratch work. If your scratch work is there, then I don't mind that at all. Yeah, Eric?
Do you care about like how we like get our guess for what the sequence is going to converge to? Can we just write down, oh, this is going to be 1, or would you like to see something?
I think if it's obvious to you, it'll be obvious enough to me, so I'm okay if you just want to state the claim straight off. Yeah, that's totally fine. Totally fine. Okay, great. So we have some good examples there. Okay. Okay, let's talk about a few other things. So now I do have to go at 5 for sure, but I have time to do a few more examples. So this will be fantastic. What number am I on? Is it number 5? Number 6 already. Okay. So let's do a couple of things with supremums and infimums here. So let's do number 6. Okay. Assume that f of x, f is a function from R to R with absolute value of f of x less than b for all x in R, and b is just some positive fixed real number. Okay, this is just another way of saying that f is a bounded function, so the graph of this function would stay in some strip, horizontal strip of width from negative b to positive b. Okay, so let's just say that. So then here's part A. Prove that if there's also another function g, which has the same condition. So assume that f and g both have this same property. So I have two different functions. The absolute value of f of x is less than b, and the absolute value of g of x is less than b. Okay? So let's do this. Let's prove, part A, proved. So we have two bounded functions. They're both sandwiched between some strip of points. Okay? Prove if f of x is less than or equal to g of x for all x in R. Okay, so if f is always less than or equal to g of x, then the infimum of the image of f, the infimum of the image of the function f is less than or equal to the infimum of the image of g. Okay, so the greatest lower bound of the function f is less than or equal to the greatest lower bound of the function g. Does this make sense? Okay. Great. How do we want to prove that? Maybe we can give names to these things. Maybe I'll call this one alpha, call this one beta maybe, just to have some notation there. Okay, so just label them that way. Here's the problem. Okay. So alpha is less than or equal to every single f of x value. And beta is less than or equal to every single g of x value. I actually gave you a homework problem that's very similar to this, that you've already done. Where, let's see, what was it? A was a subset of B, and you proved that the inf of B was less than or equal to the inf of A. Remember that problem from the recent homework? This is similar, it's just being done in the context of functions. So this alpha is less, go ahead.
Do we show that alpha is the greatest? Do we show
Greatest.
Alright, is the greatest of f?
So by definition, if I call this alpha, it is the greatest lower bound of all of the f of x's. So it is less than or equal to all of the f of x's. So think with me. If alpha is less than or equal to all of the f of x's, what else can you say about it?
It's a lower bound.
It's also less than or equal to all of the g of x's, right? So note that for all x in R, this is my proof really. This is a short proof. For all x in R, right, alpha is less than or equal to f of x, which in turn is less than or equal to g of x. Okay? So alpha is less than or equal to f of x, which is less than or equal to g of x. Fair enough. So what does that tell you then? Alpha is less than or equal to g of x for all x. Okay, and so what does that tell you? Alpha is a lower bound for g of, oh, I wrote capital X here, I meant real numbers R, sorry. So, right, so alpha is a lower bound for g of capital X. Fair enough? Okay, so now I'm ready for somebody to tell me why I'm done with the proof.
Because alpha is, so beta is the increment of g of x. It's greater than all the other lower bounds.
Correct. Beta is the greatest lower bound of g of capital X. Alpha is some other lower bound, so then alpha has to be the smaller one. Okay, so since beta is equal to the infimum of g of x, alpha is less than or equal to beta. Yeah, that's the way to finish the proof. Okay? Wonderful. So that's not so hard. Just thought I would throw that at you. Let's try another problem here that has to do, by the way, it'd be really good to practice things like, supremum of, you did some of these already. There was one in the homework. So this just is something, if you're running out of problems to think of doing, if b is less than 0, you get something like this. Well, I could see myself asking a test question where I gave you the same problem, but I said let b be greater than 0. If b is greater than 0, then they're both going to be soups instead of one of each, right? So those are the sorts of things you could be thinking about. Or there's a problem I didn't assign where you take the elements of a whole set and just add a constant to everything from that set. And you won't be surprised that the formula is just that. You just take the supremum of the set itself and then add the constant to it. So stuff like that, right? So you can make up these problems. You don't need me to give you all these questions. You guys can come up with some great examples on your own. Okay? So, but let me give you another one here that is easy to get to right now. So B, if A is a subset of R, and we define A squared to be the set of little a squared such that A is in the real numbers, so we just square every single real number, prove that the infimum of A squared, I'm sorry, don't prove it. Prove or disprove. I don't know, I'm going to let you guys think about whether it's true or not. Prove or disprove. Again, I won't do this to you on the actual test, but it's either true or false. is it true that the infimum of a squared is just the infimum of a squared? These are the cool sorts of problems. So if you square every element of the set, capital A, and you ask for the infimum of the new set, will it just be the infimum of the original set squared? A lot of people saying no. So if it's no, then what are you going to do to convince me? An example. Okay, so let's think about an example here. If you think it's a disprove.
If you have an element that's negative,
So your idea is, it makes sense to use negative numbers in addition to positive numbers probably, because if you just use positive numbers, then of course squaring positive numbers preserves, the smallest thing is still the smallest square and the biggest square is still the biggest square. So using negatives and positives would be a good idea. So how could you make a set that uses negatives and positives? Say again? Negative infinity to 0. Do you want to include 0 or not? Include it? Okay. All right, let's just try that. Okay. So we take that set. What is the infimum of that set? Oh boy, now I have a problem. I don't know how to square negative infinity. Don't know how to do that. So can we think of a different set that we could make here? Okay, just make this into a number, right? So maybe just make this into like -1. Do you care if I include the endpoints or try it like this? Okay, so in this case, what would be the infimum of A? -1. And if you're giving this example, I'm not going to expect you on the test to stop now and prove that right now. It's just obvious to me. Okay, so you just state that. Okay, so the infimum of A is that. Now if I work out what the set A squared is, what would be the set A squared? 0 to 1, not include, right? Halfway open. Okay, so then the infimum of that set would be 0, right? There you go. There you go. So the infimum of A quantity squared is +1, and the infimum of A squared is 0. They're not the same. So there's a counterexample. It's a nice way to come up with a counterexample. Okay. Getting a lot of these done. Let's see what else I want to do. I've got about just 10 minutes here. Oh, this is maybe a, okay, I already talked about countable and uncountable, and I'm going to throw one at you that's a little bit harder. Thank you, Charles.
Of course.
Okay. Countable, uncountable, one more time. Okay, so is this is number 7. Is this countable? And what it is it's the power set of the natural numbers. And what that means is this is the set of all subsets of the natural numbers. It's a set of all subsets. So I didn't say whether those subsets were finite or infinite. They could be whatever, right? So one example would be the even positive integers. Another example would be the multiples of 17. Another example would be the numbers 1 through 10. Right? So we look at all of the subsets of n. Now this is a case where somebody might look at it and say, oh, natural numbers are countable, so this must be countable. But the problem is you're not really thinking about what's actually being looked at here. We're not looking at the natural numbers, we're looking at the subsets of the natural numbers. And includes the empty set too. Right? So this is a set. This set, for example, has the empty set. Then it has all of the singletons. Right? Then eventually you get all those. So you can see it's bigger than n. It feels bigger than n, I should say. I don't want to say precisely what I mean by that. Then you would take like all of the sets of 2 and so on. But it doesn't even have to be finite sets. It could be the set of evens or the set of odds or whatever. So just any subset of the natural numbers. Well, this is definitely very, very infinite.
Yeah.
But the question is it big enough to be uncountable? So in other words, you have all the singletons is already infinite. And then you're going to go back and make all these other subsets. I mean, there's a massive number of these subsets. It's much, much bigger than just n. But each subset is coming from n. See, if I said power set of the real numbers, you would know immediately that it's uncountable, because your list, even just the singletons, would be uncountably many, and then you have an even bigger set than that, right? But this is only the power set of the natural numbers. So it's definitely infinite, because there's infinitely many different natural numbers that we can make singletons out of. The question is it, how big is this thing?
Would you be able to project it with the reals? Because then, like, if you think about like the real number, like 1.0, like you could make a real number out of each of the entries in the set. So
Okay, you're on the right track. We can make a bijection between these guys and, of course, so we can make a bijection between these guys and something else that we already know about. Let me show you how to do this. This is one of those things. Once you see it, you'll be like, oh, that's so easy. So I'm going to make a bijection. I'm going to send the empty set. I'm going to draw, if you don't mind, I'm going to draw I'm going to draw some strings of numbers here. I'm going to do it vertically instead of horizontally. So to the empty set, I'm going to associate the infinite string of zeros. Okay. To the natural numbers, the whole n, I'm going to associate a string of ones. Okay. To this element, I'm going to map that. So I'm defining the function right now. I'm going to map this to 1, and then 0, and 0, and 0, and 0, and 0, all the way down. For 2, I'm going to go 0, 1, 0, 0, 0, 0, all the way down. Okay, keep going like that. The 3 would be 0, 0, 1, 0, 0, 0, 0, 0, 0, like that. For 1, 2, I'm going to do 1, and then 1, and then 0, and 0, and 0, and 0. The elements that are actually in the set, those positions I'm making into a 1, and the other positions are zeros. So like with 1 and 3, the first position, yep, there is a 1, there's not a 2, there is a 3, and then 0, 0, 0. Okay, for the evens, you would do 0, 1, 0, 1, 0, 1, 0, 1, because the ones are in the evens positions. And then for the odds, you would do 1, 0, 1, 0, 1, 0, and so on. Say again? 16? Oh, up here, you're not going to have the same numbers multiple times. This is just a list of distinct elements of a set, right? Are you guys understanding this? If I take infinite strings of zeros and ones, is that countable or uncountable? So I'm not really using quite your idea, because you wanted to do a bijection with R. And this is not R, but this is infinite strings of zeros and ones. I think it was a Homer problem. To work with the problem, wasn't there a problem about infinite strings of zeros and ones in the Homer?
Yeah.
I think you were asked to prove that it was uncountable. And the idea was that you do the Cantor's diagonalization argument again, except instead of having 10 different digits, you only do it with these 2 digits. So you can basically create a bijection from F to S, which is the set of all infinite strings of zeros and ones. Okay? And then you just have to explain. So if it's a bijection, then these are either both countable or both uncountable. But this one is uncountable by the homework. Does that make some sense? Okay, so that's kind of how that works. What I'm going to do, as I'm kind of out of time for today, as it turns out now I have a lot of things I've got to go do. I'm going to post some additional problems and solutions on my website. I got through a lot of these actually. I'm going to go post some more with solutions and let you guys look at those. And then I'm going to do another review on Tuesday evening when I won't be rushed at all. So if people want to talk for 4 hours on Tuesday, I could do that. And I might be able to go through some more of them, but I don't know that you'll need that. I really think we did a pretty good job. We talked about a lot of different things here. Really practice with images, pre-images, bijections, that kind of stuff. That's a good thing to work on. And then of course the sequences material, using the limit theorems. Those sorts of things I think will be helpful as well. But I think I'm going to pause for today, if that's all right, and get on the road. Okay? Thanks for coming.